In this video, we'll be going through question 12 of the 2024 HSC Mathematics Extension 2 exam. Part A. The vector A is 1, 2, 3 and the vector B is 2, 0, negative 4. Part A wants us to find A dot B over B dot B times B. Now, before we jump into this question, you might recognize that this expression A dot B over B dot B times the vector B is actually equal to the projection of vector A into the direction of vector B, or onto the direction of vector B. Okay, now we don't need to know that for part I, we're simply computing the value of that expression. And so we go ahead and take the dot product of A and B, that's going to be 1 times 2, plus 2 times 0, plus 3 times negative 4, which is minus 12, divided by B dot B, which is actually the length of B squared, so that'll be 2 squared plus 0 squared plus negative 4 squared. Now all of this in itself is a scalar, and we're multiplying that by the vector 2, 0, negative 4. So I have negative 10 in my numerator, and I have 20 in my denominator. So this scalar out the front is actually equal to minus a half, and I can multiply each component of my vector by minus a half to get my final answer of negative 1, 0, positive 2. And that's our vector there. Now part 2 says, show that A minus A dot B over B dot B times B is perpendicular to B. Now this is an interesting question because I would assume that a lot of students would actually just use the values of A and B given to them in order to work this out, and that would be perfectly fine. That's what the question's asking. But if you understand the geometry of the projection, you can actually prove this is true for any vectors A and B. Maybe we can exclude the 0 vector, but for any non-zero vector A and B, this is actually true. And I'd like to show you why this is the case. If we have this set up here, we have a vector in black, which is in the direction of B. That's why I've called it KB. We have another vector, A. Then this green vector is going to be the projection, which is exactly that expression there, which is what we worked out in part I. So this vector in green is the projection of A onto the direction of B. And I'll just write that that's equal to A dot B divided by B dot B times B. Well, what's A minus that vector? A minus that vector is this orange vector here. And this orange vector is perpendicular to the line that the vector B lives on. So this vector is A minus A dot B over B dot B times B. So one thing that we could do is we could simply just say B dotted with this vector A minus A dot B over B dot B, B. Let's consider what this is equal to. Hopefully we can show it's equal to 0, and that proves that these two vectors, I should say, are always perpendicular, regardless of what the vectors are. But if they're true for all vectors, then they're certainly going to be true for these two vectors, because this is just a specific case. So I'm going to expand this out. I'll get B dot A. This entire expression here is simply a constant. It's just a scalar. So when I take the dot product of this vector with this vector, the scalar can move out the front, and I'm really just taking the dot product of B with itself. So we'll end up having A dot B divided by B dot B. That as a scalar multiplies with B dot B. Then I can see that B dot B cancel, and I'm left with B dot A minus A dot B, and that's equal to 0, because of course the dot product is commutative. It doesn't matter what order I take the dot product. So now that I've showed that the two vectors dot to equal 0, I'm going to make a concluding statement to explain what that means. So since B dotted with a minus a dot b over b dot b is equal to, times b is equal to 0, then a, not a, it should be b, b is perpendicular to a minus a dot b over b dot b times b. And that's the end of the question. We've proven it in the general case, so it must be true in the specific case. Part B. Use partial fractions to find the integral of 3x squared plus 2x plus 1 over x minus 1 times x squared plus 1. Okay, we want to use partial fractions, so let's go ahead and set it up. We have our integrand, which is x minus 1 in the denominator, x squared plus 1. I need to split that into partial fractions. So it's going to have one fraction with a denominator of x minus 1 and one fraction with a denominator of x squared plus 1. Now, my numerator here will be a constant, and my numerator over here will be a linear function, bx plus c. Okay, now I just have to determine the values of a, b, and c. So I'm going to make a common denominator, and when I do that, my numerators should be identical. So a times x squared plus 1 plus bx plus c times x minus 1. The first thing I'm going to do is let x equal to 0. That'll give me the coefficient or the value of x. So when I let x equal to 1, my left-hand side is equal to 3 plus 2 plus 1, which is 6. My right-hand side is equal to 2a, and so I get instantly that a is equal to 3. So there's one of my values. Now I have to work out b and c. There isn't really a value that I can sub in that will just give me one of those, so I'm going to compare coefficients here. I think I'm going to go for the coefficient of x squared first. So I'm going to write the coefficient of x squared. On the left-hand side, the coefficient of x squared is just 3. And on the right-hand side, the coefficient of x squared comes from a times x squared and from bx times x. There's no other way to get it. So I've got a plus b. But of course, a is equal to 3. So I have 3 equals 3 plus b, which means b must be equal to 0. And to get c, I'm going to look at the constant term. So for the constant term, which is really the coefficient of x to the 0, on the left-hand side I have 1. On the right-hand side, the constant comes from a times 1 and from c times negative 1. So it should be a minus c. Now if a is equal to 3, that means c is going to be equal to 2. So now that I've decomposed it into partial fractions, I can go ahead and compute the integral. So the integral of 3x squared plus 2x plus 1 divided by x minus 1 times x squared plus 1 dx, that's going to be equal to 3 on, not 3, it's going to be equal to the integral of 3 on x minus 1 plus 2 on x squared plus 1. Now these are both quite simple integrals to compute. This will be 3 log x minus 1, and this will be 2 tan inverse of x, and of course I have a plus c. Okay, that's part B done. Let's have a look at question C. It says, consider the equation, the modulus of z equals z plus 8 plus 12i, where z equals a plus bi is a complex number and a and b are real numbers. Part I wants us to explain why b equals negative 12. Okay, so I have this expression, or this equation. The modulus of z equals z plus 8 plus 12i. And I want to explain why b is equal to negative 12. Okay, well, z is a plus ib. Let me go ahead and put that in. And what I might do is I might just collect the real and imaginary parts together so that I have a plus 8 and b plus 12i. Now, if I don't really know what to do here, by the way, you'll notice that I haven't subbed it into the modulus of z. But if I don't really know what to do here, the question actually gives me the answer. It tells me that b equals minus 12. I just have to explain why that's the case. But if I think about what happens if b equals minus 12, this expression becomes 0, and it becomes a purely real number. So there's a 0 imaginary component. So I can maybe potentially argue that this number is purely real, which it is, because the modulus is just the length of the vector that the complex number represents. And so that is going to be a real number. So what we'll say is we equate the imaginary parts on both sides. And what do we get? We get that 0 equals b plus 12. And I might justify this. I'll say because z is a real number, modulus of z is a real number. And so therefore, b equals minus 12. Okay? Now part 2 says hence or otherwise find z. Well, now that I know that b is equal to minus 12, I can sub that back into this equation with z equal to a minus 12i. So I'll have a minus 12i equal to a minus 12i plus 8 plus 12i. Okay, now this is going to be equal to a squared plus 144. The square root of that will be equal to a plus 8. I'll square both sides. A squared plus 144 equals a squared plus 16a plus 64. Now it's just a matter of solving a simple equation. 144 minus 64 is 80. And so a is equal to 5. But the question didn't ask me for what a was equal to. It asked me to find z. So therefore z is equal to 5 minus 12i. Always make sure you answer the question. Part D. Explain why there is no integer n such that n plus 1 to the power 41 minus 79 times n to the 40 equals 2. So let me write that equation down. n plus 1 to the 41 minus 79 n to the 40 equals 2. Okay, and we're told that n is an integer. Okay, so this seems like they've used large powers here so that you don't go ahead and expand things out. And if you did do that, you'd be probably spending the rest of your time doing that. You would run out of time in the exam. So there needs to be some sort of argument that we can do, which shouldn't be too long because this question is only 2 marks, but it should knock out the question pretty simply. And one thing to consider is that when you're dealing with integers, is that you can do a bit of casework. And your 2 cases would be when n is an integer that's even and when n is an integer that's odd. So I'm going to say, in our first case, I should say case 1, let's suppose n equals 2k for some k an integer. So I'm supposing that n is even. Well, what happens if n is even? Then 2k plus 1 to the power 41 minus 49 times 2k to the power 40 equals 2. But this is an odd number raised to the power of 41. So what we're doing is we're taking an odd number and multiplying it by an odd number 41 times. So that's going to remain an odd number. And here, I've got one factor of 2. I've got many factors. I've actually got 40 factors of 2. But as long as I have one factor of 2, this number automatically becomes even. So I've got an odd minus an even, which should be an odd number. But the claim is that it's equal to 2, which is an even number. So my left-hand side is odd, but my right-hand side is even. And that's obviously a contradiction. So I'm going to flesh this out. I'm not going to just say contradiction. I have to explain what I've done here. I'll say 2k plus 1 to the power 41 is odd. And 79 times 2k to the 40 is even. So therefore, the left-hand side equals odd minus even, which is equal to an odd number. But the right-hand side equals 2, which is even. And so we have a contradiction. So it's not possible for n to be an even number. All right? But it might be possible that n is an odd number. So let's check that case. Case 2. Suppose n equals 2k plus 1 for some integer k. We're really just going to play the same game here. So I'm going to substitute this in, and I'll end up with 2k plus 1 to the 41 minus 79 times 2k plus 1 to the 40 equals 2. It's going to be the same argument. Here, I have 2k plus 2, which is an even number. I might actually write that. 2k plus 2. You know what? Let's even factor out the 2 to make it super explicit. So this is to the power of 41. This is 2k plus 1 to the power of 40. 2k plus 1 is odd. So now I've got that even minus odd again is equal to even, which is a contradiction. But I'll make the same argument. 2 times k plus 1 to the 41 is even. And 79 2k plus 1 to the 40 is odd. So my left-hand side equals even minus odd, which is odd. But the right-hand side equals 2, which is even. So therefore, we have a contradiction again. So it's not possible for n to be even. It's not possible for n to be odd. That means n can't be an integer. There's no integer which will satisfy this equation here. Okay? So therefore, no value of n from the integers satisfies the equation. And that's the end of that question. So now we move to part E. The line L passes through the points A, 3, 5, negative 4, and B, 7, 0, 2. Part I wants us to find a vector equation of the line L. Okay, so I need, for the equation of a line, I need the position vector of a point on the line, and I need the direction of the line. So let's work out the direction of the line. If it has to pass through A and B, then AB is a potential direction of this line. So that's going to be equal to 7 minus 3, 5 minus, 0 minus 5, 2 minus negative 4. Well, I'm reading things wrong. 2 minus negative 4. And what's this equal to? That would be 4, negative 5, 6. That's the direction. And then we can pick either A or B to use as our position, or to use as the point whose position vector we're going to use in the line. So it doesn't really matter which we pick. I might just pick A just because. We've got 3, 5, negative 4 plus lambda times this direction. Okay, and I'll say where lambda is a scalar. I should say that because I should specify what lambda is. If I've introduced a lambda, I should tell everyone what that is. Now part 2 says determine, giving reasons, whether the point C, which is 10, 5, negative 2, lies on the line L. So this is part 2. We have the point C, which is 10, 5, negative 2. Now if C lies on the line, I should be able to sub in the position vector for C into R, and I should be able to find a value of lambda which makes that a true statement. So I'll say if C lies on L, then there exists a lambda such that, subbing it in, 10, 5, negative 2 is equal to 3, 5, negative 4 plus lambda times 4, negative 5, 6. Okay, well, if this is true, then that means 10 would be equal to 3 plus lambda, or 4 lambda, let's put the 4 out the front, 3 plus 4 lambda. 5 would be equal to 5 minus 5 lambda, and negative 2 would be equal to negative 4 plus 6 lambda. So if it lies on the line, there should be a value of lambda which satisfies all three of these equations. However, we can see that from the first one, we would get lambda equal to 7 on 4, and from the second one, we get lambda equal to 0. And so straight away, that's not going to work out. There's no value of lambda that satisfies both of those, or all three of those, let alone the first two. So therefore, there is no value of lambda which satisfies the equation. And so therefore, C does not lie on L. And that's the end of part E and the end of question 12.